Good afternoon. Welcome to the summer workshop on plasma physics, and I'm Swarniv. So today we are going to learn on our seventh lecture regarding the scaling and normalizations of a set of differential equations in plasma physics. Well, what is plasma scaling? You see, in plasma, the spatial and temporal extent vary from different orders, from many orders of magnitude. Okay. Nevertheless, there are significant similarities in the behavior of apparently disparate plasmas. Now, while we want to understand the scaling of the plasma behavior, it is more related to the uh, application aspect rather than the mathematical aspect. By the way, mathematical simplicity is also carried out if we scale our equations. The situation is similar to a testing of an aircraft or studying the natural turbulent flow in wind tunnels with small models that we do in our aerodynamic laboratories. Now, plasma scaling, often known as similarity scaling, uh, help us to work out the plasma properties and how they change in the order to retain some of the characteristics. There may be some properties which are very well understood or investigated if we are in a very small scale of measurement. So, first step to they express the law of governing equations of the system is in the non-dimensional form, because if there is no dimensionality or the dimensions, then only the physics part is included, and those orders of magnitude what we have observed in a smaller scale and missed in our bigger scale of measurement is included in such a study with normalized equations, and it is usually only possible by achieving a choosing of uh, certain certain quantities that will normalize our system. Now, for instance, let's give you an example. Since there are suppose a plasma is composed of ions and electrons. Now, an ion, suppose a proton is consider it to be an ion. Definitely, it's plus charge. So it's almost 1836 times more than the electron. So if we divide these two ratios, then we get a factor of 1836. It is commonly taken to infinite. We while dealing with the atomic model, initially in our lower classes, we studied that the nucleus is infinitely heavy and the electron moves around. But as we came to college, we understood that the whole system moves about the center of mass, and the mass of the nucleus is high, is large, but still finite, and therefore those correction terms in the Rydberg term and Rydberg factor and all these things are taken into account. So in numerical studies, often we studies the opposite problem often appears. What? The computation time would be interactively large if a realistic mass ratio is used. You see, if 1836 times mass ratio uh, times mass of ion is considered, so then the computational hazards are there in the problem. So mm, we just divide it with that factor. So to analyze some of the phenomena such as the lower hybrid oscillations, it is essential to use proper value because they are the exact frequency, uh, and all these things are important. Now I have written here commonly used similarity transformation. You see, you will find this in the net, and you see that length, time, and all these things, capacitance, they are scaled by a factor of x to the power 1. That is uh, by their values. And particle energy velocity, it's x to the power 0. But by the way, this chart won't help you in while uh, starting the normalization and the transformation thing. But I would say that if you go through an example that I will carry out in the next part of this lecture, it will be very easy for you to understand. Okay. So the plasma scaling, this scaling applies best to plasmas with a relatively low degrees of ionization. Highly ionized plasmas, in such a case, these things are a bit complex. We'll deal with this later. In such a plasma, the ionization energy of the neutral atom is an important parameter and establishes an absolute energy scale which explains many of the scaling in the table and the previous table. Since the masses of electrons and ions cannot be varied, the velocities of the particles are also fixed, as is the speed of sound. If velocities are constant, then time scales must be directly proportional to distance scale. In order that charged particles falling through an electric potential gain the same energy. Why? Because the electric field potential difference is same. So if the charge is same, then it will gain the same energy. The potential must be therefore invariant, implying that the electric field scaling varies inversely with the distance. So another thing is that assuming that the magnitude of the electric field cross B field, that is E cross B field, is important and should be invariant, the magnetic field scale must be scaled like the electric field, that is inversely with the size. This is also the scaling required by Faraday's law in uh, electromagnetic theory and the Ampere's law as well. So I think so far you haven't learned about what is Alfvén wave. So this kind of change, hmm, this kind of scaling factor is done in the Alfvén wave. Assuming that the speed of Alfvén wave is a magnetohydrodynamic wave. Hmm. So we will study in later part of the course, and it must remain invariant. The ion density must be scaled with B square, magnetic field square, that is inversely with the square of the size. Now, in regions where quasi-neutrality is violated, this scaling is required by Gauss's law, okay, and not by Ampere's law. And Ampere's law also requires that current density scales inversely with the square of the size, as we have previously discussed, and therefore that current itself is invariant. So one of the con, uh, constant of motion or the system, we can call it the current. The electric conductivity is current density divided by the electric field, because we have the Ohm's law, um, J is equal to sigma E, okay, and thus electric conductivity also scales inversely with the length. In partial ionized plasma, the electric conductivity is proportional to the electron density and inversely proportional to the neutral gas density, implying that the neutral gas densities must scale inversely with the length, and the ionization fraction scales inversely with the length. So all these things, so many conditions we are discussing one after the other. It might not get into your head instantly, but once we start normalizing the problem or set of equations in the example, it will be clear for you. Okay, but this scaling has also got some limitations. Well, they have some basic properties of plasma. So not all plasma phenomena can be scaled in this way. For instance, the degree of ionization, which is a dimensionless and thus would ideally remain unchanged when the system is scaled. The number of charged particles per unit volume is proportional to the current density. Definitely is proportional, because current density J is equal to NeV, which is proportional to N. The number of charged particles per unit volume is proportional to the current density. So which scales as 1 by x square, whereas the number of neutral particles per unit volume scales as 1 by x in such a transformation. So the degree of ionization does not remain unchanged but scales as x to the power minus 1. You see, you make a product or a division of these two things, it becomes x to the power minus 1 or 1 by x scaling. Now let's come to an example, and let's start with these basic equations. Is handwritten, So I think if you have any problem, please check the lecture now. Okay. So you see, this one is the continuity equation of the. This is the continuity equation of the electron. It is the continuity equation of the ion. And wait a minute, where is the cursor? It is the continuity equation of electron, continuity equation of ion. This is the momentum equation of electron and the momentum equation of the ions. And this is the Poinson's equation. Before we come to the later part, let's describe all this part. This whole term, two terms, is a convective derivative. This is the charge of electron by mass of electron, del phi del x. You see, I haven't put here bar. It is just phi. But these are all unnormalized. If it is normalized, then we put bar. But later when you carry out the problems, after normalization, writing the bar over your variables all the time is really irritating. So you just skip the bar and just write the variables as it is, provided the normalization has been done and the set of equations is scaled accordingly. Now 1 by mn MENE, that is mass of electron, density of electron, del PE del x, h square by 2 me square del del x, 1 by root over NE del square root over NE del x2. Now as I have said, this term is the bomb potential term or the quantum diffraction term. Now, some of you have asked that, sir, why in some cases we are just neglecting this? We are not neglecting it. In such a problem, the quantum diffraction term has not been included. You see, whenever you are studying something, if the density of the particle is very high, then this quantum diffraction term is taken into consideration. But if the density is moderate, then we just skip this term. Even then, the pressure is also taken as a classical pressure. But here we will take the quantum pressure, that is the Fermi pressure. Since we consider this system to be very compact, very dense, having particles of the order of 10 to the power 28 or more per centimeter cube. 10 to the power 28 particles per centimeter cube or more. Now this is the ions momentum equation. You see, here we have put the same thing, but I is in the suffix ui, and qi by mi, and see h square by twice mi square del del x 1 by root over ni del 2 root over ni del x2. Now this is the Poinson's equation. Now as I have said, this is the pressure corresponding to the jet species. Jet species means either ions or electrons. Now it is mass times velocity, Fermi velocity of the jet species squared, nj cube by 3 nj0. That is, this is the equilibrium density. For ions, for electrons, it would be Pe is equal to me Vfe square Ne cube by 3 Ne0 square. And for the ions, accordingly. Now, for these terms, let me write this. The charge of an electron is minus E, where E is 1.6 into 10 to the power minus 19. In some of the articles, you will consider the charge of electron itself taking E. So, charge of ion would be minus E because they have included minus 1.6 into 10 to the power minus 19 as E. But here we will take the numerical value. So, for electrons, since it is negatively charged, we will include the minus sign. So, you can see the charge of the ion is plus E. H cut is the reduced Planck constant or Planck constant divided by 2 pi. So here we will introduce the normalization scheme. You see, in the normalization scheme, x bar, that is the normalized space, is equal to x omega pe by VFE. You see, if you check the dimension of this quantity, it is equal to 1 by x. It is 1 by time, it is velocity by time. Since velocity is in the denominator, velocity will remain in the denominator and time will go in the numerator. So these two cancel out, only 1 by x. So this is dimensionless, this one is dimensional. Time is normalized with electron plasma frequency. This is This has got the dimension of energy. K into Fermi temperature of electron, and K is the Boltzmann constant, is the has also got the energy of dimension of energy. So this is the Nj. The particle densities has been normalized with their equilibrium values. So and the velocities have been normalized with Fermi velocities of electron. Remember, here we have taken only Fermi velocity of electron and not of that of ion, since we have taken here J and not Fe, because velocity should be on one term, only one quantity. Now let's go for the expression of Fermi velocity. Pfe is equal to twice 2 times Fermi energy of electron by mass of electron. Now Fermi energy of electron is written in terms of particle density. Okay, here it is often the expression that you will get in the internet or in other books, where n is the total number of particles and v is the enclosing volume. So total number of particle by volume is equal to the equilibrium density. So it is n is 0. So h cut by me, h cut square by 2 me, 3 pi square n is 0 to the power 2/3. If I substitute here in terms of EF, we get the Fermi energy in terms of density, equilibrium density. So this term is your practice, you can just check it yourself. Well, remember, velocity is equal to momentum by mass. Why did I include this section? You will check. You see, h cut by this whole quantity has a dimension of momentum, because momentum by mass is equal to velocity. Now this quantity has got the dimension of wave number. How? You see, it is number density, that is number per unit volume. If you go here, it is number, it's a pure number, it is volume, that is 1 by length cube. Now what is 1 by length cube? Has in this we have this 1 by dimension 1 by L cube. So if I take the 1/3 of it, this is 1 by L, and 1 by L means uh, having a dimension of wave number, that is 2 pi by lambda, as we find K. So it has got the dimension of wave number. This is just for your consideration. Now plasma frequency of electrons that we have used in a normalization is 4 pi n is 0 e square, charge of electron square by mass of electron. Okay, let's come. Now starting with the normalization scheme, now I have to just reverse the process. That is, we have to write the unnormalized term in terms of some factor times the normalized term, because in such a case, in place of d dt or del del t or del del x, we can just put del del x bar with this factor. We have just got the transformation written in the reverse way. That is, the unnormalized terms is written in terms of the normalized and the normalizing factors. Okay. So starting with the continuity equation, because that will be very easy for you. Del n bar del t bar, because n bar has been uh, normalized with the equilibrium value. So n bar, n is 0, and t was normalized with, as you see, by omega p, by omega p. So it would go in the numerator. So it is n is 0 omega p. Similarly, here we check for this thing del del x bar. So if it is x bar, it is VFE by omega p. Okay, for the x bar, that is the space coordinate, we have made this change. And for density, we will use the equilibrium density, and for the velocity or the fluid velocity, we will use the Fermi velocity. So this if cancels out, you see both these terms has got the same normalizing factors multiplied. Okay. Okay. Similarly, for ions, we will get on both sides Ni0 omega Pe. Since this term can never be 0, the whole term is considered 0. And this equation without this term is the normalized continuity equation for electron, normalized continuity equation for ions. Okay. Now start with the momentum equation. Start with the momentum equation. We have this velocity normalized multiplied by Fermi velocity, then whole thing becomes unnormalized. Starting with the unnormalized equations, we are just substituting with the normalized quantities multiplied by the normalizing factors. Simply we have done for t, and here you will, I just missed initially by writing, so I u e del ue del x, that term, because we have in the numerator 2 times ue, so vfe square, and for x we have vfe omega p. So this one of these square terms will cancel out. So in the left hand side of this momentum equation, which is vfe omega pe, both sides, and let me check for each of these terms. So we have just written it e by me. We have just put phi and x here. This is the phi factor with due to phi. This is the vfe by omega p for x. Similarly, we have done these things 1 by me as it was. So with this normalized density, the equilibrium density, and for the pressure. Now for pressure, I have put it like this. But if you simplify it, it will be more easier for you. Okay. But before that, okay, let me simplify first. So PFE, it is given, PE of electrons Fermi pressure in one dimension is given by this expression. If we normalize these things, you see, everything, this NE is the only thing that need to be normalized. So it is normalized, and in the NE0 cube would be there. So cube, and there was one square in the denominator. This would cancel out, so it is only NE0. So this factor into NE cube. Now it is that 1 by NE bar, some factor, this factor into del n cube del x bar, del n bar cube by x bar. So when we differentiate it, we get 3 ne square, and that ne will cancel out with 1 ne. So it is n del x. That's kind of expression. Well, come with the bomb potential or quantum diffraction term. Come with this thing. Now, this was all initially there. Now I haven't included this because you see it is n bar here, n bar here. So whatever be the factors of the equilibrium densities, they will cancel out. And the denominator, there is no x 3 times, 2 times here, 1 time here. So we'll just write that factor, multiplicative factor, cubed. Okay. Now left hand side, as we have seen, that factor comes here, we have seen. So I am just not VF omega p in both the terms, it is there. So you just write on the left hand side. On the right hand side, we start with this factor del phi del x 1 by n. This is the whole thing, and here we have written in terms of q, and here the potential term, bomb potential term. Okay. Now starting with the first factor, you see E by m, we multiply with this factor due to phi. See, E cancels out, 2 k TFE omega p VFE. Now let's check here. Half m VFE square is equal to Boltzmann constant times Fermi energy of electron. Now if we multiply 2 here, so 2 k T, we put these things out here, twice me VFE square instead of 2 kt. There is me, this me is out here, omega APE by VFE. So everything cancels down to give the same as the factor on the left hand side. Okay. Now the second factor, that is the statistical pressure term. You see 1 by me, and you just put that factor that came with the pressure term. So me cancels out, ne0 cancels out. There was VFE square in the denominator due to x, there was VFE, cancels out, and this was the term which looked like this. Now if we differentiate it, 3n square, this and this will cancel out, and this 3 will cancel out. So it is omega p VFE times ne del x. This is the same factor as the left hand side and the first term on the right hand side. Okay. Now third term on the right hand side, this was the factor. This was due to 3 times putting the x in the denominator, and this was the normalized terms. Now we have said this thing like this: h cut omega p Hmm? And we have taken 1 omega p here out and multiplied both by VFE. So 1 would be in the numerator and VFE to the power 4 would be in the denominator. So we have made it square. So it is h cut omega p by me VFE square. Now you see this has got the in dimension of energy. We know Planck's constant, reduced Planck constant times the frequency is the energy, and this has also got dimension of mm, firm energy. So let's introduce a new variable known as the quantum diffraction parameter term or constant h. Why did I put it h? Well, some initial authors have started with h, so you all are doing with h. That's the thing, nothing more. You can just put anything. There is no hard and fast rule. Okay, just one. Now half mv square is the energy is equal to kb TeF. Therefore, the third term becomes this whole quantity on the right hand side becomes h square. This is normalized multiplied by the same factor on the left hand side and on the first and second term on the right hand side. So you see that the whole equation has been normalized. Okay. Now start with the iron equation. We will do the same thing, and here we get the same term on the left hand side. Now start with these quantities on the right hand side. You see there was Me in the previous case, it is Mi. Now expand it like the same way, and you will find here one Mi here, one Mi here, one Mi square here. The rest, well, here is one Ni0 which will cancel out ultimately, nothing more. So as I have carried out the elimination again and again, I'm just not including in the lecture. So you see, you multiply it with Me. If you multiply, because that energy that we were introducing was below as Me VFE square, the ratios. So if we multiply numerator and denominator with Me, so this quantity comes as mu, and this was the Fermi energy of electrons as usual, and we have used the same kind of normalization in the case of iron, but only this factor mu comes. Okay. Now the second term on the right hand side, here is this Mi cancels out. Well, VFI by VFE. Now when VFI and VFE, you see we write in terms of uh, Fermi velocity and Fermi temperature, we get these factors. It is one Mi by Me. Therefore, Fermi temperatures ratio is Mi by Me times VFI square by VFE square. Now, if in this factor VFI by VFE square, it is equal to mu times sigma. So, the second term on the right hand side would become this factor. This is the same normalizing factor. This is the multiplicative factor. Now, someone was asking in the group that, sir, why don't we just use dimensional analysis? Well, in dimensional analysis, you miss some factor terms like this mu, sigma, all these terms, and you are just left with the raw equation without those factors. Well, the mathematics doesn't change for that case or this case, but you have to be exact on your normalizing scheme. So it is that multiplicative term. Now come to the third term of the equation. It is h square Mi square. You see, now here Mi square. In previous case for electron, it was Me square, and we said the whole term comes out to be h square by 2. Now here Mi square, if I multiply with Me square here, this becomes Me square by Mi whole square, Me square. This whole term, as we have said, what? It was h square. So half, it would become half mu square h square, half mu square h square, that normalizing factor with that with this normalized expression of the function. So the same constant on the left hand side. Now we are done with these things. Let's just recapitulate a few. Let's get it one page view. Come on. So these are the normalized equations, five normalized equations. This is the pressure term or the equation of state. These are the normalizing factors. Okay. These are the velocity and the frequency terms that we will be using in the normalization. Those are the crucial things because that defines how your problem is set and what are the detailed study you can carry out. It's very important while choosing those things. Okay. And we have given the expression of Fermi energy, Fermi velocity, and starting with those normalization we just get the unnormalized terms in terms of the normalized quantities with some factors, and thereby we substitute it in the dynamic equations in terms of x, t, phi, u, all these things, and get these normalized equations. This is the first part of the normalization. Then you see v omega, you just remove these parts. Okay, whenever it has been normalized, these materials on both sides will cancel out. So the normalized set of equations will look something like this. Well, I will just check it for you. Mm. Just the normalized set of equations. You see those five equations are written in complementary equations, and the normalized set of equations will look like this. Let's zoom it a bit. Okay, and those ions and electrons continuity equations will be the same. So we have just merged it into one. We have written here there was one mu missing, just included, or here one typographic error. Forget about that. So the set of equations will look like simple. You see, you don't have those constant terms, and your all those parameters are included in these constant terms, h, mu, sigma. Okay, so we have done those things as we have carried out, which every term on the right hand side of momentum equations. Okay, now come with the Consensus equation. Well, I missed it. Consensus equation. You see del 2 5 del x 2. So we just replace this term for phi, this term for phi, and this term for x square. So you will get a quantity like this, which after simplification and putting the value of omega pe will come out to be 4 pi ne0 e. You see 4 pi ne0 e on the right hand side. So this quantity just vanishes out, and you just write del 2 phi del x2 is equal to ne minus ni. That's as simple as anything. Okay, now let's close this lecture. Okay, thank you for your attention. Therefore, normalization of a set of differential equations is for the simplicity of execution of the mathematical treatment, and also to deal with the scaling terms that we have discussed in the first part of the lecture. Thank you.